Hello everyone, welcome back. And in today's video, we are going to solve a few AITS problems. So let's begin with the first one. So in this question, we have uniform rod of mass capital M and length L. It is hinged at the center O and it is located in a vertical plane. A solid ball of mass small m and radius capital R having initial angular velocity of omega naught and moving vertically downward with a velocity of v naught collides elastically with the rod at a point A, which is located at a distance of capital R from the center O of the rod. The coefficient of friction between the cylinder and the rod is given to be mu. So we have to find the angular velocity of the rod and the ball after collision. Okay, so give this problem a try, guys, and then check out the solution. Okay guys, so this is how the initial situation is given to us. So the ball is falling with a velocity of v naught and it is rotating with an angular velocity of omega naught about a horizontal axis passing through its center. So now let's try to write down what are the forces acting on the ball while the collision is happening. Okay, so when the ball and the rod come to contact with each other, there is obviously normal force acting between both of them. So first we have the normal force. Let's call it as N. The point of contact of the ball and the rod are slipping relative to each other, right? So the contact point of the ball is slipping towards the left. So friction force will act on the ball in the rightward direction. So there will be a friction, a force of friction acting towards the right on the ball. The same force F will act in the left direction on the rod. Okay, so these are the only impulsive forces acting on our system. So we can ignore mg because it's not going to be impulsive. So the small contribution to impulse in the while the collision is happening is negligible. Okay, so now let's say after collision, the ball rebounds with a velocity of v1 and its angular velocity is omega 1. And guys, if you observe something, as there is friction acting on the ball while the collision is happening, it will also have a horizontal velocity. It'll have a vertical velocity of v1. It'll also gain a horizontal velocity, which let's just call it as v2. Okay, and let's say the angular velocity of the rod after the collision finishes is omega 2. So now let's write down some equations. So first, equation for the rod looks the easiest to write. Okay, so let's write down the angular impulse theorem for the rod. So the only impulse that is changing the angular momentum is the impulse due to normal, right? So the angular impulse due to normal will be the impulse due to normal times capital R, and this would be equal to change in angular momentum about the point O, which is I omega 2, and I here is ml square by 12 times omega 2. Okay, so this will be equation number 1. So now as a collision is given to be elastic, we can say E equals 1. So the velocity of approach between the points of collision is simply V naught. V naught equals, so after collision, the ball moves away with a velocity of V1 and the rod has a velocity of R omega 2. So as you guys can see, the contact points are separating at a rate of V1 plus R omega 2. So this would be equal to V1 plus R omega 2. And now let's write down the equations for the ball. The impulse provided by the normal will actually change the momentum of the ball in the y direction. Impulse due to normal. So the impulse due to normal equals change in momentum in the y direction. So initially it was moving with a velocity of v naught in the downward direction, and finally it is moving with a velocity of v1 in the upward direction. So change in momentum will be small m, v naught plus v1. So the magnitude of change in momentum is v naught plus v1. Okay, so the directions are not important, so I'm just ignoring it. So now from these three equations, if you guys observe, the unknowns are Jn, V1 and omega 2, right? So we can solve for all of them. After solving these three equations, we get the value of omega 2, which is the angular velocity of the rod, as 20 radians per second, and V1 as 6 meters per second. Now omega 2 was the angular velocity of the rod, so that is 20 radians per second. So now we have to determine omega 1. So now we're gonna write down the rest of the equations, which included the friction basically. We wrote down all the equations for the normals, right? Now we can say the impulse due to friction will be equal to the change in linear momentum of the ball. So we can say Jf, which is also equal to mu times Jn. As the ball and the rod are constantly slipping, we can write friction F as mu times n. So which means Jf, I can also write as mu times Jn. The change in linear momentum, which is going to be mv2. Okay, and again we can also write the angular impulse. So with that I can say mu jn, which is the impulse times the distance from the center, which is capital R. So this is the angular impulse, and this is equal to the change in angular momentum, which will be ICM, which is 2 by 5 mr square, times the change in omega, which is omega naught minus omega 1. Okay, so again I'm only interested in the magnitudes. Now one more thing, guys. So this mu jn, I can also write it as integral of mu n dt. So jn is simply integral n dt, so I can write it this way. equals m into v2. So now let's say guys, the collision starts at time t equal to 0 and it lasts till time t equal to t. So the collision is happening between 0 to t. Okay. Now the thing is there are two possibilities, and possibility number one is that as the collision starts, friction will start acting because these 2 points are slipping relative to each other. Okay, so there is one possibility that the slipping between the ball and the rod, it stops at some time t star which is less than t. In simple terms, the slipping stops before the collision is over. So okay, so if this is the case, then the thing is friction force will only act till equal to t star, or basically until the slipping stops. After the bottommost point of the sphere comes to rest, friction won't act anymore because the slipping has stopped. So somehow we have to figure out if case 1 is what is actually happening or not. So for that, first let's just assume that the slipping stops before collision is over. So basically it starts pure rolling. So this is the initial situation, guys. So it's falling with v0 and omega naught. So we assume that finally the sphere gains a velocity of v2. So let's say it has some horizontal velocity of v2 and its angular velocity is some omega 2. Okay, so we are talking about t equal to t star here when rolling starts. So if rolling starts, so we can easily say that v2 will be equal to r times omega 2 because of the rolling condition. So now let's try to figure out v2 and omega 2. So the best way to do this is actually conserve angular momentum about this particular point over here, which lies directly below the sphere. So let's call this point as O. So again, this is a fixed point in space, guys. I'm not considering a point on the rod. Okay, I'm just considering a fixed point in space. So about point O, I can write the angular velocity as m RCM cross VCM plus ICM times omega, right? M RCM cross VCM would simply become 0, right? Because that's the reason of choosing a point directly below the center of mass. Velocity vector and the r vector, they're anti-parallel. So this would just become 0. The angular momentum about O of the ball simply becomes ICM into omega. And another advantage of choosing this point O is that while the collision is still happening, the normal reaction force and the friction force are passing through the point O, right? So we can say the net torque acting on the ball while the collision is happening is 0. So the net torque is 0. So we can simply say the angular momentum is conserved. So the initial angular momentum is simply again ICM omega. So that will be 2 by 5 m r squared omega naught, and final angular momentum. So finally, again guys, it starts pure rolling. That was our assumption. So when it starts pure rolling, this is simply like the instantaneous center of rotation, which means I can write the angular momentum about O as I about the instantaneous axis of rotation times omega. So all we have to do is add mr square. So this will become 7 by 5 mr square, and from here omega 2 comes out to be 2 by 7 omega naught, and omega naught was given as 35. So this becomes 10 radians per second, and v2 is simply r omega 2. So this comes out to be 2 meters per second. So this is basically assuming pure rolling starts. This is what v2 and omega 2 will be, and once v2 and omega 2 reach this value, it won't change because there is no friction anymore. Remember guys, friction was the one which was changing omega 2 and v2. Once friction is gone, they won't change anymore. So now let's try to determine the impulse that would be required to go from this stage to this stage. So here we determined the impulse due to friction as m into v2, right? Impulse of friction in this particular case comes out to be m into v2, which is 2 Newton second. Okay, so the in the first page we determined that the impulse due to normal is 16 Newton seconds. So now guys, if we assume slipping never stops, then basically friction will act throughout the collision, right? In this case, we can actually say the impulse due to friction will be mu times the impulse due to normal reaction, and mu is given to be 0.5. So half of 16 is 8 Newton second. So the maximum possible impulse due to friction is 8 Newton second. And if you observe for the rolling case, we obtained that. So guys, the impulse required for rolling is less than the maximum impulse that is possible. So which means the slipping will clearly stop before the collision is over. And we know that once rolling starts, we know the value of omega and v, right? So once rolling starts, omega is 10 and v2 is 2. So the angular velocity of the ball will be 10 radians per second, and it will not change. So basically the final angular velocity, which we took it as omega 1, will be 10 radians per second. So this was the solution to this problem. Now let's move to the next question. Okay guys, so in this question, we have a uniform magnetic field whose magnitude is B naught, and it exists everywhere in a long, thin-walled, hollow, metallic cylinder parallel to its axis as shown in the figure. The length L of the cylinder is much larger than its radius, so it's a long cylinder basically, and the radius is much larger than D, which is basically the thickness of the cylinder. Okay, the resistivity of the material is given to be rho, so we have to neglect the flux linkage with the material of the cylinder. And now it's given that the magnetic field is switched off. We have to figure out how is the magnetic field varying with time in the hollow part, and also how the induced current varies with time. Okay, so now let's start discussing the problem. Okay guys, so let's say I'm considering the cross-sectional view, and in this view the magnetic field is coming out, and it's given that the magnetic field is switched off, which means dB by dt will be negative, or in short the magnetic field is going to decrease, right? Okay guys, so now the thing is, we know that whenever we have a time varying magnetic field, we have around the space surrounding the magnetic field, we have non-conservative electric fields developing, and we can figure out the magnitude by using Faraday's law, which states that the loop integral of E dot dl equals minus d phi by dt. So again, we are more interested in the electric field in the material of our conductor here, because that's where the electrons will be flowing, right? So we want to figure out the force acting on the electrons, which is going to be because of the electric field. So let's try to determine the electric field near the material of the conductor. So this distance, so the radius is given to be smaller and the thickness of the material is given to be small d. Okay, so now again it's as we know that small d is much smaller in comparison to smaller, we can find the electric field at smaller and assume it remains almost constant for this whole region. So again we know that E at any r is symmetrical, so we can take it out of the loop integral, and this just becomes E times 2 pi r, and the right side becomes so the area is constant, so that will be pi r squared times dB by dt. So from here we get the magnitude of the induced electric field as r by 2 dB by dt. Okay, so now in order to figure out the direction, we'll use Lenz's law. So we know that the magnetic field is coming out of the page and it is decreasing. So in order to support the decreasing magnetic field, we need electric fields to be circulating in the counterclockwise direction, right? So the electric fields is going to be in the counterclockwise sense as viewed from above. Okay, so now what the electric field is going to do is move the free electrons present on the surface of the conductor, and they will start moving so as a counterclockwise current is developed. Okay, so now we can use Ohm's law to figure out that current. So let's get rid of this. So by using Ohm's law, for a conductor we can say J, which is the current per unit area or the current density vector, equals sigma times the electric field which is pushing the electrons. So in this case, it's the induced electric field that is pushing the electrons around the conductor, and the direction of current is in the circumferential direction. So we can easily say J is nothing but sigma. Now sigma I'm going to write as 1 by rho, because that is what is given to us, times the electric field, which is r by 2 dB by dt. Okay, so now we have the current density vector. Its direction is obviously in the circumferential direction or in the phi cap direction. Now how do we determine the current? As you guys can see, J remains constant, right? I mean, it is varying with time, but it is not varying with cross section. So we can simply say the current that is cutting any cross section, current is nothing but the charge cutting the cross section per unit time, right? So we know the current density is current per unit area. So I is just going to be J times dA. Here the cross section through which current is cutting is this particular cross section. So that has an area of D multiplied by the inward length L, right? So the cross section I'm talking about, so this is the cross section that I'm talking about. So it has a length of L and the thickness of it is D. So, and current is cutting this cross section. Okay, I mean, this will be integral J dot dA, but J is constant with respect to positions, so I can just take it out. So this is just going to be J times A, and J is again, so this will be 1 by rho times r by 2 dB by dt times the area, which is L into D. Okay, so now we have the current. So now somehow we have to get rid of the current and bring it in terms of the magnetic field. And for that, we are definitely going to use Ampere's law. As this thing is, as we can model this long cylinder as similar to how we model solenoids, we are going to take a rectangular Amperian loop. Okay, again the current is in the circumferential direction. So the current cuts the Amperian loop, something like this. And we know that as this is a very long solenoid, we can consider the magnetic field outside to be approximately 0. And these two sides won't have any components for B dot dl because the sides are perpendicular to the magnetic field. And the magnetic field inside is going to be uniform everywhere. And let's say its magnitude is B. Okay, and we're talking about some arbitrary time, right? As we know, the magnetic field is changing with time. At some arbitrary time, let's say magnetic field inside is B. Now we can apply B dot dl in this loop. So that just becomes B times L, and this will be equal to mu naught times the enclosed current. Okay, so we know that the current passing through the entire length L of the cylinder is I. So the current per unit length, which we call it as the surface current density, K, is nothing but I divided by L. So that is basically the current passing through per unit length of the cylinder. Okay, this should be capital L. Okay, now B into small l equals mu naught times the I enclosed. So the enclosed current will be the current per unit length times the length of the Amperian loop, which let's just take it as small l. Okay, so this will be mu naught times surface current density, which is current per unit length, times L. So from here, we get the magnetic field inside the cylinder as mu naught I divided by L. So from here we can say I is BL by mu naught. So I just turns out to be BL divided by mu naught. So now substituting I into this equation, we'll get this value for dB by B. Okay, as we are dealing purely in terms of magnitude, this equation is also considering that everything is positive. Okay, but we know for a fact that the magnetic field reduces with respect to time. So we have to put a negative sign here. Okay, so from here, after integration, we can see that the magnetic field is an exponential decay. After integration, the magnetic field comes out to be this particular value, and the current is simply L by mu naught times this particular value. So the options A and C are correct for this question. So now let's move on to the last question. Okay guys, so in this question we have an AC circuit and the voltage is given to be 120 sine of 100t, and we have to match the columns. So we have to figure out the peak current through the source, so basically the total current, right? So we have to figure out the total current I, then we have to figure out the current through R2, which means the current in this branch, potential drop across AB, and then the average power across R3. So we are going to be using the complex number method to analyze the AC circuit. We'll discuss a few concepts before solving the problem. So let's say when we are given a sinusoidal voltage, let's take a random one of V0 sine of omega t plus phi. So you guys might be knowing, if you write the KVL equation for this loop, then you have to solve a very complicated you'll have to solve fairly complicated differential equations. You have to make multiple equations and the differential equations become quite complicated. So what we do instead is we use phasors to simplify our analysis. So I'll explain what phasors actually are. So in simple term, what a phasor actually is, it is a complex number which basically contains information about the amplitude and phase of our sinusoid. So let's understand it a bit further. So here I'm going to be using the Euler identity. So e to the power iota theta, we know it is equal to cos theta plus iota sine theta. So this thing over here, V0 sine omega t plus phi. So if I want to express this V in terms of complex numbers, I can write it as the imaginary part of V0 e to the power iota omega t plus phi. So as you guys can see, if you open up e to the power iota omega t plus phi and take its imaginary part, you will get sine of omega t plus 5. Okay, so these two expressions are actually identical. So now what I'm going to do is I'm going to split the exponential into two factors, e to the power iota phi multiplied by e to the power iota omega t, using simple properties of exponents. And this term over here, V0 e to the power iota phi, is what we term as a phasor. And in this case, it is basically the phasor of the voltage, right? I am going to term the phasor voltage with the symbol V, with this symbol. So this is simply V and a curly sign over it. And this curly sign is called tilde, okay? So V tilde is nothing but V0 e to the power iota phi. So again, coming back to our original point, it has information about the amplitude and phase of the sinusoid. As you can see, it has the amplitude and the phase. okay, and it is independent of the time, as you can see, because that the factor involving time was e to the power iota omega t, right? And now if you want to go back to the sinusoid from our phasor, then what you have to do is to the phasor multiply e to the power iota omega t and take the imaginary part, okay? And remember guys, this imaginary part is, we're taking the imaginary part because it's sine, it's a sine function. If it was a cos function, then you would take the real part, right? Yeah, just keep that in mind. So now the usefulness of phasors is that we can basically treat this entire circuit. It just makes this circuit solving much easier. So we can use all the tricks that we learned to solve DC circuits, provided we convert everything into phasors first. So in this problem, again, as you can see, the voltage source is given to be 120 sine 100t. So the phasor voltage in this question, it will come out to be 120 times e to the power iota 0. Now clearly we want the total current, right? So one of the options actually mentioned it. So if it was a DC circuit, then what we actually do is we try to figure out the R equivalent, right? Then we do V by R and then we'll get the current. So, and here the ratio of V by I is something that we call as the impedance. So impedance is nothing but the ratio of the phasor voltage and the phasor current. Okay, so it is also again a complex number, and most of you guys might be familiar with the result. So for the inductor, the impedance we call it as XL. It is called the inductive reactance, and this is equal to L omega, but there should be an I in front as well. Okay, so the magnitude of XL is L omega, but in terms of complex numbers, if you want to write, there should be an I in front. Okay, and XC is going to be 1 by C omega, but here the iota is in the denominator. Okay, the derivations for this, if you guys want, I'll make another video of it, but it'll take too much time if I cover this right now. So the impedance of the circuit, we can it has two parts. First part is the resistive part. So this basically includes the resistances of the circuit, and then we have the imaginary part, which includes XL and XC basically, right? So so this part is also called as a reactance. So this is the complex part. Okay, so these are the only information we need to solve this problem. So now we can start solving the problem. Okay, so in this question again, omega is given to be 100. So we can determine the XL for this inductor to be 0.3 times 100, which is 30 ohm. And for this inductor, it will be 20 ohms. Now we can use similar methods we use in DC circuits. L and R1 are in series. So the impedance of this branch, let's call it Z1, we can write it as, again, the resistance is the real part of the impedance, which is 20, and then we have the imaginary part, which is XL in this case, so that is going to be 20, but again XL has an I in front. Okay, so now for this branch Z2, let's say, is going to be the resistance, which is 20, and guys, you can figure out XC. You can do 1 by C omega, it will also come out to be 20 ohms. Okay, and here also the reactance is 20, but again XC is 1 by C omega I. So, and 1 by I, you can also write it as minus I, guys. Okay, so this you can also write it as 1 by C omega minus I. Okay, so always write XC with a minus sign. So this will be minus 20 I. So now we can use the formula for parallel resistances. So when two resistances are in parallel, the Z equivalent becomes Z1 Z2 upon Z1 plus Z2, and if you multiply these two complex numbers, it is A plus B times A minus B, so that will be 800. If you sum it, it will be 40. So this comes out to be 20 ohms. So the impedance comes out to be real. So this entire part simplifies as 20, and now we have to add another 10 ohms to it. So the total impedance becomes 20 plus 10, which is 30. Then we also have an XL of 30 ohm here, so that will be 30 I. So the final impedance becomes 31 plus iota. Okay, voltage phasor V tilde was equal to 120 e to the power iota 0. Okay, so now let's try to convert 1 plus iota in the Euler form. Okay, so for that we can divide and multiply by root 2. The reason for doing this is cos 45, this is sin 45. So we can write this thing as e to the power iota 45. So this becomes 30 root 2 e to the power iota 45 degrees. So now we can relate the voltage phasor and the current phasor similar to how we write V equal to IR. So this will be V tilde equals the current phasor I tilde times the impedance. So the current phasor comes out to be 120 e to the power iota 0 divided by 30 root 2 e to the power iota 45. So this comes out to be 2 root 2 e to the power minus iota 45. When you divide two exponents, their powers subtract, right? So now we have the current phasor, guys. So as I said earlier, the way we convert a phasor back to the sinusoid is we multiply e to the power iota omega t, and in this case we'll take the imaginary part. Okay, so if you multiply e to the power iota omega t to it, it'll just get added up in the powers, and then we take the imaginary part. So we'll finally get the real current, sinusoidal current, as 2 root 2 sine of, because we took the imaginary part, omega t minus 45. So this is the final current phasor. So as you can see, it lags behind voltage by 45 degrees, right? So now in the options, they actually wanted us to figure out the peak value, which is the amplitude, which is 2 root 2. Okay, so P matches with 4. Now they're asking us about the peak current through the resistor R2. Okay, so let's assume for a second this is a DC circuit and we have two resistances in parallel. As they are in parallel, the potential drop across these two branches is the same. So we can say I1 R1 equals I2 R2. Or in other words, we can say that I into R is a constant. The current divides in the inverse ratio of the resistance, basically. So the current in the R2 branch, which is what we are interested in, so let's call the current as I2. So I2 will be proportional to Z1, right? So I2 is in current division in parallel branches that we learned in DC. We can directly write it as Z1 divided by Z1 plus Z2. And remember guys, this is again the phasor current. We're doing all of the impedance operations with the phasors, right? Impedance itself is a complex number. So it will be Z1 upon Z1 plus Z2 times the total current, which is I tilde. So in DC, like if this was R1 and R2, the current through R2 will be R1 divided by R1 plus R2 times the total current. So this is exactly similar to it. So now let's try to figure out Z1. So Z1 is 20, 1 plus iota. Z1 plus Z2 is 40. And I tilde from here, it is 2 root 2 e to the power iota minus 45. This will cancel out and this will be 2 that cancels out with this. 1 plus iota, again I'm going to divide by root 2 and multiply by root 2. 1 plus I by root 2, I can write it as e to the power iota 45. Root 2 times root 2 becomes 2, and there is an e to the power iota minus 45 left, and I tilde just becomes 2 e to the power iota 0. Okay, so now again, where we go back to the sinusoid I2 is again just, so we multiply e to the power iota omega t to it, and we take the imaginary part of the phasor, which is e to the power iota 0 multiplied by e to the power iota omega t. So this is how we get the sinusoid back, and this just becomes 2 sine omega t. So the peak current through R2 becomes 2 amperes. Okay, and in option 3 they are asking us about the peak potential drop between A and B. So we figured out the impedance between A and B, right? So that is simply the impedance of this entire thing, and that came out to be 20 ohms. So the potential across this is going to be, will be I into Z basically. So VAB will be equal to the total current I times the, again this is also phasors, so V tilde across AB is equal to the current I times ZAB. So this comes, so ZAB is simply 20, right? It doesn't have any imaginary part. So if you multiply it with the current, it will come out to be 40 root 2 e to the power minus iota 45. So now if you convert it into the sinusoid, it will be 40 root 2 sine of omega t minus 45. So VAB comes out, the peak value comes out to be 40 root 2. So R matches with 1. And the last question they're asking is about the average power dissipated in resistor R3. So R3 is over here. So we know the current that flows through R3 is I tilde, right? Now guys, the average power, well, if you want the instantaneous power across R3, let's call it P3. The instantaneous value will be the sinusoidal voltage V to the sinusoidal current I. So this will be the instantaneous power. The average power across 3, which is basically the power in across one complete cycle. This comes out to be the RMS current squared times the resistance. Okay, so in this case, we know the current that is flowing through it, right? It is I tilde. So the magnitude of the current is 2 root 2, right? So if you divide by root 2, you'll get the I square RMS. So that'll be 2. So 2 squared will be 4. Resistance is 10, and this comes out to be 40 watts. So the average power dissipated is going to be 40 watts. So S matches with 2. So that was it for today's video, guys. If you enjoyed the video, please do like, share, and subscribe. And that's it. Thanks for watching.